Yeah, so welcome to lecture number 1, Introduction to Lattice Boltzmann Methods in the winter term 24-25. I was going to say to most of the students that this may not be the easiest lecture during your lifetime, yeah, but it can be one that is maybe a little bit more interesting than others, hopefully. We learn here about the Lattice Boltzmann, the theory, mostly the theory of the Lattice Boltzmann methods. And in this, we mostly focus on things that are not in the book or in the books that are around. Yeah, so we'll. It's certainly useful to look into some books. You can decide yourself which I mean here, but the stuff that we are covering is to a large extent not what it is in the book. Yeah? So you could see this as a little bit complementary. Today, we are not talking about the Lattice Boltzmann method. So if you came today for this, I'm sorry to tell you, we start with something else. And the thing we are starting with is a short introduction to this kinetic theory, where the Lattice Boltzmann method is rooted in. Yeah? So important to know, you don't need to understand kinetic theory in order to understand the Lattice Boltzmann method. And many practitioners just don't. Yeah? Which is completely fine. Yeah? But then whenever there is reference to kinetic theory, this could be a little bit confusing. So what we do today is we are talking about the background with kinetic theory, and then going on later lectures, we actually come to the Lattice Boltzmann method. I hope nobody is now disappointed. Yeah? So it's very interesting because you don't get this thing in other lectures, I believe, at least here in most of our subjects. So, kinetic theory, there is this visual abstract that I just removed here, yeah, that distinguishes between 3 different ways to see the world: an atomistic view, a kinetic, and a continuous. So I'll repeat this here. We have an atomistic view. So the atomistic view is that we have particles with mass mi and acceleration ai, which is equal to the sum of the forces between particles. So the forces of the particles j acting on I. Probably have to make this a vector. So what you have here, say, these 4 particles, 1, 2, 3, 4, and what happens is that there are forces in between all of these. So, and these forces lead to an exchange of momentum, and by this also an exchange of energy between the particles. And from this arises, of course, what we observe in nature. Yeah? So what is special here is that we have distinct particles, and they follow Newton's laws. Newton's laws of motion. Okay, this is a very successful description. important here, and even though this may sound very natural, because how would you do it otherwise, is that there are distinct particles. Distinct particles means every particle has a name, yeah, and you follow each particle by its name. Okay, so this is the atomistic view. And this can, of course, also be modeled. For example, in molecular dynamics, there you have a list of particles, 1 to a million or a billion, and you follow all of them, and each of them has a name, yeah? Or at least an index. So we can distinguish these particles. So then there is the other, you could say, extreme. This is the continuous description. And for fluids, which we're interested here, in here this is usually then described by the Navier-Stokes equation. And I have a little bit the hope, even though I cannot know for sure with all students, but I have the hope that you are a little bit familiar with the Navier-Stokes equation, but we'll talk, during the lecture we'll talk a lot about it, so let's write it down in short notation. So we have a time derivative of a velocity vector u plus a so-called advection term. So this we call the material derivative, which I hope you had already the opportunity to learn in other lectures. We are teaching this in some of our classes on fluid dynamics. So this is on the left-hand side, and then on the right-hand side we have a pressure term. So there's 1 over the density times the gradient of P, which is the pressure, and then there is a viscosity term on the second derivative, so Laplace operator on velocity, yeah? Pressure potential. And back here we have diffusion. So this is what the Navier-Stokes equation is made up of. We have a material time derivative, so we have a time derivative in the material form. So material derivative of the velocity is equal to the gradient in a pressure potential and a diffusion term. And this thing is called, I mean, we call this continuum because it is augmented by a continuity equation, which is the time derivative of the density rho is minus the density rho times the divergence of the velocity. So this is actually this equation we call the continuity equation. So we have continuity and we have the momentum equation. So this is called the momentum equation, even though we have written it down here in velocity form. So of course, for incompressible fluids, the time derivative of rho would be 0. Okay, so this may be familiar. So this description describes a fluid. Fluid is a Okay, so every first lecture I do, I have to tell my students that unfortunately I'm dyslexic. So if I write a stupid nonsense, yeah, just try to imagine what I actually meant, yeah. Obeying conservation of mass mass momentum. What we often forget is, and maybe because this is a little bit trivial, or is trivially conserved, is that this also conserves angular momentum. And one thing that surprisingly it does not conserve, which is why I put this here in brackets, is energy. So of course nature conserves energy, and you can also augment the Navier-Stokes equation with an equation for the energy and make it energy conserving, but the Navier-Stokes equation is only on an equation for the momentum. So it in itself does not conserve energy. And the reason why it does not conserve energy is because the diffusion term drains energy out of the momentum and would usually put this energy into thermal energy. So it would increase the temperature. Yeah? So since there is no temperature in this equation, energy is not conserved. Okay, so these are the two common ways how we talk about matter, yeah, or liquid matter, or also, yeah. So we have or the world in general, as you wish. I mean, you either describe things with a continuum theory, where you have a partial differential equation. Yeah, this you can do with fluids and with solids. Yeah, or you describe them in terms of these atoms. Yeah, so you know both of them are kind of, yeah, I don't know, kind of true or kind of what we learn. It's a little bit strange because you always think what is actually in between. So why do we have these two possibilities? And the thing that, in a sense, is in between is this kinetic picture. By the way, no, I wanted to add something. I wanted to add something here. Let's just see in my notes. Right, the atomistic picture that we had, that was the first one. So the atomistic worldview is actually not very old. It has only been accepted, and I find this strange, and I wonder whether you actually know this, that this is a thing from the 20th century only. It's surprising because in ancient Greece 3,000 years ago they were talking about atoms, yeah, but maybe because they did this, maybe because it was done in antiquity, it was never forgotten that it was done in antiquity. Modern science of, say, the 19th century regarded this as mythological, yeah? So that they would say this is like, from a modern point of view, this would be like you're a flat earther. So in the 19th century, if you believed in atoms, you were like you believe in flat Earth today. Yeah? So there were these people, and I have a few citations actually, but I will only write down one. So I have there's no political meaning in that I'm now citing Nietzsche. Sorry, I just think that Nietzsche was a public intellectual in the 19th century. Yeah, nothing to do with what his worldview was, other than the physical worldview. So in his book Beyond Good and Evil, we find the following line: as far as materialistic atomism goes this is one of the most well refuted things in existence. And it goes a little bit on, but I'll leave it there. I mean, it is interesting that somebody that a public intellectual and philosopher felt the need to actually write this down, which means that there were actually people around who believe in atomistic. This was just not the scientists. Most of the scientists didn't. So actually, why we know, so the Navier-Stokes equation, for example, is a result of the 19th century, and it was developed, of course, completely without knowledge of atoms and without the belief in atoms. Yeah. So the reason why in the end we started believing into atoms is actually coming from the kinetic theory. The kinetic theory is also a child of the 19th century. Actually, it comes before we understand atomism in detail. And it is a thing that is very important for our modern worldview, but you could say it's mostly left to the physicist. Yeah, so the physicist figured this out, and everybody else then just believes it, say, yeah? So now we dip a little bit in what they said, because this is where our method that we're interested in is coming from. Boltzmann, Ludwig Boltzmann, came up with this Boltzmann transport equation, which is the equation from which we will later derive the Lattice Boltzmann equation. So we'll call this thing BTE, Boltzmann transport equation. And interestingly enough, this actually came before Nietzsche, but not that much before. This was Boltzmann, 1872. Yeah, he wrote a book, and it's all in German. So if you know German, you can actually read all of this in the original. And I had one copy of his book, of his original book, in my hand. It was in Munich. They have it in the library. Yeah, so the Boltzmann transport equation looks like this. There's a time derivative of a thing that is called f. And this thing that is called f, we'll later say this is a distribution function. Then comes something that is called xi, vector xi, which is a velocity vector. We'll cover this in detail, times a spatial, so nabla, yeah, spatial derivative on f, plus, then comes a force term. F here is a force, which we'll have to divide by the mass of a particle, and this goes, so this is multiplied again. So these are scalar products, yeah, into a nabla xi f. So this nabla xi f is will not spend a lot of time explaining this. So this nabla here is the usual spatial derivative, yeah? The vector of spatial derivatives, and this here is the vector of velocity derivatives. So we make a derivative in velocity. What we have on the right-hand side, this omega is the collision operator. So this is his equation. We'll look into the detail in a minute. So important thing here is the f. F is a distribution function that describes the statistics of where atoms are. So the important distinction to the atomistic view is that molecules are now undistinguished or undistinguishable particles. So it's very important to get this difference clear. Yeah? So if I have more students in the room, I would usually say this is the following. So you are human beings, each of you has a name. Yeah? So you are this one, this one, this one. Because there's a recording, I'm not allowed to say any names of you. Yeah? But you all are individuals and you all have your names, and it is a difference whether you are sitting there or there. Yeah? You're in a different state. So, or no, not in a, so, no, sorry, that was not what I wanted to say. So, each of you is seen as an individual. And instead of seeing each of you as an individual, I could just say there are 5 students, 10 students in the room, yeah? And then there are seats here, for example, and I could say this seat is occupied by a student, and this seat is not occupied by a student, yeah? And I'm sorry, I don't care for you individually, I just say, so there are so many students there, and some seats are occupied by students, and some seats are not occupied by students. And this F is, in fact, the probability. For example, if we stay with the probability density, yeah, of a state being occupied. If we stay with the seats, we could say, so there's a probability when I come to the lecture hall that this seat is occupied by a student or not. So usually in my bigger lectures, in the bachelor lectures, the seats at the end of the lecture hall have a higher probability of being occupied than the one closer to me. In the master lectures, the seats closer to me have a higher probability to be occupied than the further away. Yeah? Yeah, so and this is given by this probability density. So probability density of finding a particle. So now we are not talking, particles are not located in seats, but they are in a so-called state space, and the state space is 7-dimensional. Yeah. Okay, now the state space is only 6-dimensional, but the phase space is 7-dimensional because it also includes the time. So phase space. So what are the dimensions? So there's a time t, then there is a location. In 3 dimensions, the location is given by vector x, which contains x, y, and c. So this is the location. And then the particles also have a speed. And the speed is this ominous xi. And the vector xi will be combined as a scalar xi, a scalar upsilon, and a scalar zeta. I'm very sorry for these letters, but this is That's the way we usually write this. Okay, so now instead of watching the particles, particle by particle, we talk about the statistics, the probabilities of a particle being there, or being in a certain place. And this actually makes the difference between, already between point particles, yeah, and now fields, so continuous fields, because the probability is a field, yeah? So we are still talking about particles, but we already have a field, because we are not saying that the particle is there, but we say that the particle has a probability of being somewhere, yeah? And this probability can and usually is continuous. So this is why the Boltzmann equation, by the way, the Boltzmann equation is a differential, is a partial differential equation. So it has to act on continuous variables. Otherwise, you cannot take the derivative. Yeah. Okay. So then there's a statistic. Say statistics of particles instead of individual particles. I mean, one very important implication of this is, of course, you have absolutely drastically reduced the amount of information you are dealing with. Yeah? So for me, it is a much less information to say I have 50 students in my lecture, is a much simpler information than to say I have this student, this student, this student, this student, and this student, right? 50 times. So, okay, I've already said this, but let's write it down. How is the time? Is half an hour? Okay. Okay, so dTF. So this, of course, is the change in time. This is the change in time plus this xi scalar multiplied on nabla onto f. This is something that looks very similar to what we had in the Navier-Stokes equation. Yeah, in the Navier-Stokes equation, we have this material derivative, and there comes also a velocity scalar multiplied with nabla on velocity again, right? So this actually is the kinetic advection. It's a bit different from what we'll talk about this in a minute, how this distinguishes from the Navier-Stokes advection. And then what we have here is the forces. And with this term, we usually only describe long range forces. So these long range forces could, I mean, this is really what we classically describe as a force, like gravity, or for example, if we have charged particles, it would be electromagnetic forces. Yeah? So things that go a far distance. The forces, the mechanical forces that act when particles are in contact with each other, yeah, these are considered short-range forces because they act only when things are in contact. And they do not belong in this picture, what we have on the left-hand side, in this differential picture, yeah, because, I mean, they are not field variables, yeah, but they are events, yeah? So they cannot be described with this continuous field. So we have to have another term that describes these events. And this is what we call a collision. So collision are events. There's always these leaf blowers during my lecture, I hope. So they are short range, yeah, so more or less contact forces, yeah. Okay, so these are the terms in the Boltzmann equation. Okay, let's look on what we mean here by advection. Okay, how does advection work? Advection works pretty simple. Say we have a particle here. This particle has a position x and is here at a time t. So it also has a velocity. If it has a velocity, then it moves according to its velocity to, say, this position here, where it will then have x plus dx. Yeah, so it has moved the distance dx, and the time has changed from t plus dt. And then they have this microscopic velocity. The microscopic velocity is the derivative, the change of the position with time. So the microscopic velocity is the velocity of the particles, of the single particles. And particles are, of course, moving in the direction of their velocity. Velocity xi. So xi, just also write it down, is the microscopic velocity. So I need more paper. There is a very interesting distinction between the advection in the Navier-Stokes equation, as I just said, and the Boltzmann transport equation. So if we look at the Navier-Stokes equation again, so then we have here the time derivative of u comes with u dot nabla u. And what you see here, so this is the material derivative. Yeah, I hope you have seen this already somewhere else. So this advection term here, so it's moving the velocity, so it's moving the gradient of the velocity with the velocity. Yeah, what you obviously see here is that there's velocity twice in it. And this is the only term in the Navier-Stokes equation that is nonlinear. And the nonlinearity of the Navier-Stokes equation gives us a lot of trouble when we try to solve this. So this is the reason why we have turbulence in all these things. Yeah, this comes from this nonlinear advection term. So, and there is, of course, in the Boltzmann transport equation, there's also the advection. So we also have time derivative of f, and then we have xi times nabla f. So now you see this is pretty, this looks pretty similar, yeah? So in both cases we have, say, we have a time derivative, and here we have a velocity scalar product on a spatial derivative, and this placed onto something, namely the velocity, in the case of the Navier-Stokes equation. And in the case of the Boltzmann equation, this is placed on the distribution function f. But one thing is very interesting, namely that in the Navier-Stokes equation, u is a dependent variable. Yeah, it's the variable you are solving for. Yeah, this is where you're seeking the solution for. Yeah, so this also makes it here nonlinear. In the Boltzmann transport equation, this xi is a coordinate in the state space. So it's an independent variable. Yeah, so it's completely independent, and now the fun thing is here, this because this is this is just multiplied by its coordinate, this thing here is linear. Yeah, I should, the dependent variable here, the one you're looking for, is f here. So u and f, I mean the one for Navier-Stokes and the other one for Boltzmann transport equation, these are the dependent variables. And xi is just a coordinate. It's the same as with x. Xi is an independent variable. So this thing that does all the trouble in the Navier-Stokes equation is actually just a linear operator in the Boltzmann transport equation. Yeah? So this should make our life actually much simpler, but we also have the collision. And this is kind of the difficulty. I mean, by the way, you should consider that these two things, these two equations, describe the same physics. Yeah? So they also should behave the same. And now the interesting thing is on the left-hand side of the Navier-Stokes equation, we have something nonlinear, and in the Boltzmann equation it's linear. And actually you cannot describe the same thing. You cannot describe a nonlinear thing with a linear equation. Yeah? So the nonlinearity in the Boltzmann equation comes from the collision. And the collision is the thing that we spend most of our time with trying to understand. So, collision. We have to start with an assumption that also Boltzmann did, and the assumption is that there's only binary collisions. So that never three particles come together in exactly the same time. So it's basically two particles touching. In reality, this, I mean, if you think very hard about this, then it starts to matter. But in reality, if you don't look that hard, then it actually really does not matter, because you could always say that if three particles collide with each other at the same time, they behave like two particles colliding first and then the other, then one coming out and colliding with the other. Yeah, oops, what did I do? What was this? We are back. Okay, so how can we describe this? we have to go now into our velocity space. And our velocity space here in 2 dimensions has a coordinate xi and a coordinate small upsilon. Yeah, sorry, I don't know how better to write this than this. So, and in this, we'll now have collision. And I'm trying to draw a circle here. And let me see. I got one particle coming this way, and I'm going to call this particle having the velocity xi1. And then I have another particle that comes this way, and I call this, and this will come in with velocity xi2. Yeah? So I'm committing a sin here, I just noticed, because I'm giving these particles different colors. And the important assumption was we do not distinguish between these particles. Yeah? So we just say 2 coming in this way and 2 going out. We do not distinguish whether the one goes this way or the other one goes that way. Yeah? You could just imagine when particles are collided, they are destroyed and new particles are born. Yeah? We don't care whether they are the same, right? So, but they come together in this way, and then somehow two of them come out again, and I'll call this, xi2, what is it, dash, and this one, now I mixed up my colors all together, okay. So this is xi1 also dash. So the one with the dash are the one that come out of the collision, and the one without the dash are the ones that come into the collision. Okay, so this picture looks a little bit messy, and the reason for this is that we look at this in the laboratory frame. That we look at it in the laboratory frame. We'll have a nicer picture if we do it in the center of mass frame. Now I'm only using one color. So in the center of mass of the collision will always, if we look at a collision in its center of mass, then particles will always collide head on. Yeah? Because, see, if they collide at an angle, then they would then the coordinate system would not be center of mass, yeah, because they have a bias in the momentum in this coordinate system would not be 0, yeah. The sum of the two momenta. So center of mass coordinate system means that the sum of the momenta is 0, yeah. So the vectors have to have the same length, and they have to go head on, yeah, in order to cancel each other out completely, yeah. And I mean we can imagine this, that that this entire coordinate system, yeah, is then again moving in space. So it has the average velocity outside. So say this here is now incoming xi1 and xi2, and now I'm trying to improve on my inconsistency before. I'll just use the other color for the outgoing. They again, so because of energy conservation, they have to have the same length. Yeah? Otherwise they would not conserve energy. But they can move, after collision, they can move in any direction. So they say this is xi1 and this is xi2. Okay? This is the center of mass. Center of mass frame. So, now I already said something about energy conservation, yeah? So there is something strange with this mouse. There is somewhere a hidden button. When I press this, it goes to the start. I don't know where this is coming from. Yeah, so conservations, there is laws for this collision. So collision has conservation laws. So what is conserved is, for example, the number of particles. Yeah, so two particles going in, two particles are coming out, right? So this is conserved. With this, obviously, the mass is being conserved. What is conserved is the momentum. And for this, we can write an equation, right? So for momentum conservation, we can write there is a mass m. So the particles are undistinguishable. They are all nitrogen. I mean, you could have two probabilities, one for nitrogen and one for oxygen. Yeah, so this is possible. So you could distinguish between a few different types of molecules, but all molecules of the same type are the same. Yeah. So they also will have all the same mass. Yeah. So they will have the same mass, and then as far as momentum goes, so they would have the mass of the first particle and the velocity of first and second particle before the collision. They must be the sum of the momenta after collision. So this is what momentum conservation is. Angular momentum is conserved. So we don't go into detail with this, but this very simple picture, yeah, of particles going straight in and straight out, this cannot change angular momentum. Yeah? So this is trivially conserved. And what is then conserved is energy. So what we see that energy is conserved is that when we go in the velocity field, so the length of these vectors, yeah, is also conserved. So they start on this circle and they end again on the circle. Yeah, this is due to energy conservation. And energy conservation is, of course, we have 1/2 the mass of. Now energy is written as the product, yeah, as the product of the velocities. I mean, with itself. So velocity square before the collision is being the same scalar product. No, this is wrong. So it's velocity of the first times velocity of the first plus velocity of the second times the velocity of the second. Yeah? So this must be conserved. Okay. Now Boltzmann had this ingenious idea, which in the Anglo-Saxon world is called molecular chaos. Molecular chaos. Which actually Boltzmann called Stoßzahlansatz. It's actually funny that Stoßzahlansatz is translated into molecular chaos. So, because Stoßzahl, so I mean, they are both in a sense correct, but what Stoßzahlansatz means is Boltzmann Boltzmann proposed that the Stoßzahl, so this is the collision number, yeah? So it's the number of collisions in a certain space over a certain time. Yeah, you just say the only thing that describes the fluid, the behavior of the fluid, is how many collisions are there per time and space. So only the number of collisions. So this is Stoßzahl, yeah? And this is translated into molecular chaos. For whatever reason. So so let's write some texts. So colliding particles. Okay, so the idea, I think this is why it's came to be known as molecular chaos, that the colliding particles are uncorrelated. That's actually saying the same thing with different words. So, I mean, you should probably think that this makes a difference whether this particle collides or that particle collides. Yeah, so like, I don't know, when we stay in the picture with we're talking about people, yeah. So then it's important to you whether this is your girlfriend and this is your boyfriend and so or somebody else, yeah. But let's see from a population point of view, we just say, okay, so there are so many couples, yeah, that somehow have sex and get so many children, yeah. So this is the difference. So for each individual, it may look like it makes a difference. What is your spouse? Yeah? But in this picture, we say it doesn't matter. Yeah? And it does not matter because the history of what has happened before, so the particles are undistinguishable. Yeah? So put it this way. If all possible girls are exactly the same, and so much so the same that you can, at each time, you can exchange one with the other, because they also don't have memory. Yeah, so there's no memory other than their position. So if they are undistinguishable, so you don't need to care whether this is actually now your girlfriend or somebody else. Yeah. So this is the idea that the history of the particles didn't matter. Yeah, this is molecular chaos, and because they didn't matter, the only thing that now matters is the number of actual collisions. But I have to finish my sentence. Sorry. So this means velocity of particle 1 is not. By the way, the fun thing is this is not actually strictly true. Yeah, because particles carry some, even only with their momentum, yeah, and their position, they carry some memory. Yeah, so it's not true that it really doesn't matter. It's just that there are so many particles that it practically doesn't matter anymore. Yeah, if you have only a few particles, it absolutely matters what happens between them. Yeah, but if you have many particles and they see each other, so the assumption basically is that one particle has collided with one particle and they never meet each other again, and they also don't meet a particle again that previously met the other particle. So the memory, the detailed memory is lost. Yeah? Yeah, so of course this is only true if there is enough particles. Okay. This is his assumption, and in order to understand this better, we use a parametrization. Okay, I seem to be it seems to be necessary that I speed up a bit. Actually, since I only have very interested students, I don't know whether I have the right to take more time. I don't know. You have a lecture afterwards? Sorry.
Personally, we don't. I mean, I don't.
Okay. Okay, I try to finish this and don't hurry too much. Okay, right. So we want to rewrite this a little bit by a parameterization. We introduce a vector that gives us a direction. So this vector just can be in any direction, but it has length 1. So this is done in order to write the post-collision state like this. So the post-collision velocity, the post-collision velocity can be written as a combination of the center of mass velocity. So the center of mass velocity is the average between the velocity of the particles, obviously, plus now the difference 1 and 2 so the difference between them, and we take the absolute value and multiply this by a direction. Yeah? So what is the idea behind this? Okay, I write the other one too. So xc2 after collision is xc1 plus xc2. So this is the same center of mass, and now the only difference is that this here is going the opposite way. Okay, so basically this is what a collision does. Yeah, so this is conform with momentum and energy conservation. Yeah. So we have two incoming velocities, and the outgoing velocity is the center of mass velocity plus any random change in the direction where one is going this way and the other one is going in the opposite direction. Yeah? So this actually describes all possible collisions or all possible outcomes of the collision. Yeah, we just need to determine this sigma. Yeah? Or actually, we cannot determine the sigma. The sigma is, of course, random. Yeah? So it's because in a collision is a random event, so they come in and they go out in any possible direction. Okay, for completeness, write that this is center of mass. Center of mass. Center of mass and end of paper. So this is something, so this description here is useful to actually write our collision integral. So collision integral omega is also, the collision is a change in the distribution function due to collision. Yeah? So it's not, there's also a change due to advection, but this is only due to collision. And this can be written down, and I'm sorry that this may not fit in a single line. So this is the integral over all the directions. So sigma, I write now a capital sigma. Yeah, this is supposed to be all directions. All directions. and over all velocities of the particle we are colliding with. This is why, so this is a capital Xi. The other one was a small Xi. This is all the speeds. But important, not the speed of, not the speed Xi1, but the speed Xi2. So this is the particle, so we look at what particle 1, yeah? And we combine this. So we look at it could collide with all particles of velocity Xi2. Yeah? So we basically integrate over all the particles or the probability that the particle comes with velocity Xi2 and all the possible outcomes of directions where they may turn towards. Yeah? So this is, and yeah. Okay, and this goes into a kernel. There's this thing that would bother us a lot if we would deal here with real kinetic theory, but now it's not going to bother us a lot. So we say this kernel, so the kernel is something like well, when do they actually interact? Yeah, it depends on the size of the molecules. Yeah, so it's their diameter and so on. Yeah, and maybe if they have an odd shape, yeah, could they fly? Yeah, could they fly just so to miss them? Yeah, so this probability that they collide. Yeah, this of course depends on their difference in velocity. Yeah. So if, for example, they have the same velocity, they won't collide. Yeah, they will always go parallel to each other. So they need to have a different velocity. Yeah, and it could also depend on the direction. Yeah, how they are oriented could be. Yeah, is not the important thing. So this does not fit in one line. This is why I multiply this here with this here. So there is this collision kernel, and this collision kernel is now, of course, multiplied by the probability density that particles 1 and 2 are colliding, and this here, okay, this here is actually the outcome of the collision, because this is the velocity after the collision of particle 1 and particle 2. So we are looking at the probability that there is a particle is velocity Xi1 and the velocity Xi2. Yeah? We need this probability to actually have this collision, but this is the outcome. And this is minus the ingoing. I'm going to write this down. Say Xi1, so this is the incoming. I guess I probably finish all of this and then I say something. So we integrate over Xi and we integrate over Xi2 and we integrate over all directions. So what we are looking here is we want to see the change of the probability to find a particle with the velocity Xi1 when there is collision. Yeah? So then we have a kernel that describes how big the particles are. Yeah? So this is how they interact with each other. Yeah? This is in here. And then this down here is whether there are actually two particles. So for example, if the probability of a particle Xi2 would be 0, so if there is no chance that you have a velocity, that you have a particle with that velocity, then this here would turn to 0 and nothing would happen, right? And this, by the way, this comes with minus, and this is the loss term. So why loss term? So when particles when there is a particle with xi1 and xi2, yeah, and they meet, then they are scattered out of this state. And as far as these undistinguishable particles go, you could actually consider these particles to be destroyed. Yeah? So particle meet, they are removed from the probability density. Yeah? So when the particle with velocity 1 has met the particle with velocity 2, then there is a collision, then they are removed out of the state of velocity 1, yeah, because it has moved. So now when it's removed from velocity 1, then they are not really destroyed, they are just moved to another velocity. Am I too loud?
No.
Sorry.
The velocity should be less, right?
No, not the velocity should not be less. Not less. I mean, I'm sorry, I'm crying. So usually I'm talking to big rooms, so I don't to get me down. No, the velocity is not going lower. Yeah, so two particles collide. Yeah, and we are looking. We are in this state space. Yeah, velocity is a coordinate for us. Yeah, yeah. So we look at particle velocity at this velocity where we're integrating. Yeah. Or for velocity xi1, we are not integrating over this, but we're integrating over velocity xi2. So we are integrating over all possible other velocities, that could meet with a particle at velocity xi1. And all of this, when they collide, they will kick this particle out of velocity xi1. Yeah? And whenever a particle is kicked out of velocity 1, it has to be kicked somewhere else. Yeah? And it will be kicked to velocity xi1 dash. Yeah? So this is why we have a gain term. Yeah? So we lose something, and then this is put back in the gain term. So, and this is Boltzmann's collision integral. I have a few things to write down about the kernel, the collision kernel B as a function of the relative velocities. So in collision, it's the same thing when in your car. Yeah, in collision, it's always important what is your relative velocity to the thing that you're colliding with. Yeah, and it can depend on direction. Okay, well, we don't go into detail. Okay, so what I've said, the gain term particles scattered into velocity xi1, and the loss term is particles scattered out of xi1. Okay, two more things, and I believe we probably have enough time, but I don't want to rush it now. Conservation laws in the collision. So, of course, as we already discussed, collisions has to conserve certain things. namely mass, momentum, and energy. So, and this is described in the following way. So zero because there's conservation. If we integrate over the entire velocity space xi1, remember the other integral, the collision integral, is an integral over xi2, yeah, the other velocity. Now we integrate over xi1. Xi1, the collision operator, times something what we call a kernel function again, but this is not the collision kernel, but this is a moment kernel, so it's much, has a different meaning. This this kernel is a function of xi1, and we integrate the entire thing over xi1. Now, this phi could be either of the one that is just 1, so the function is just 1, or it could be xi1, or it could be xi1 times a scalar product with itself. Yeah? So, and if you put either 1 here, and you do the integral, you get 0, and if you get 0, you have conservation of mass. If you put xi1 here, and you do the integral, and you get 0, you have conservation of momentum. If you put xi1 scalar product with itself, here you do the integral, you get 0, you have conservation of energy. Yeah? So this is the idea. And we call these things here moments. So an integral of a distribution okay, I should write nicely. Of distribution F with a kernel phi is called a moment. And we spend most of our time here talking about moments. So the collision integral has 5 conserved quantities. So by the way, that it has 5 conserved quantities means that in general, if you put anything else for the kernel than this, yeah, any other function of xi in here, and you do the integral, then usually you won't have 0, because these things are not conserved. Yeah? So if you put something that is not conserved in here, you get a non-zero integral. Yeah? It's not just that the integral is 0 because collision is 0. I mean, yeah. I mean, collision can be 0. Yeah, we come to this. Later. Yeah, okay. We come to it. I will do it. But this is not in general the case. Let me see. What is the time? Oh, I look at my papers. Will take over time today. I guess I'm talking too much. Okay, sorry. So, by the way, the primitive variables, if you do fluid mechanics, then you know what primitive variables are. The primitive variables in continuum theory, this is the velocity and the pressure. and they are actually moments of the distribution function. Or the moments in kinetic theory. So, for example, particle density. So there is something where I always mess up the notation is, and I'm going to mess up the notation this year too, I'm very sorry. So the probability density function, yeah, is usually the probability of finding something somewhere. You could also say there's a probability of finding mass somewhere and then multiply this by the mass of a particle, and then you would actually get the density in terms of mass per cubic meter, yeah, what is usually the density. Now it's only a probability, a particle number density, so it's the number of particles in a certain volume, not the mass of the particles in a certain volume, yeah? And this gets a little bit messy because we simplify a little bit our notation and say, okay, this is the mass, just multiply it by the mass of a particle, yeah, and then you are done. And often this is not written down, and so we come to a little bit confusing notation sometimes. So I'm not writing times mass, but if you integrate the distribution, if you just integrate the distribution function itself, C1, yeah, so then you just find the probability that a particle is there at all. So, and in this sense, is so, and if you integrate over a larger volume, you can say, so how many particles would be there in this, yeah? So, and this is the zero moment. So it's a zero moment in the sense because it is the velocity c to the order of 0, so that you get 1, yeah? So we describe this here by their exponent, yeah? So this is this xi1, this is order 1, and xi times c is order 2, yeah? And 1 is order 0 because it's c by the power of 0. Does this make sense?
You mean by integrating? So when you
not by integrating. It's just so you put here polynomials. Yeah, these are polynomials. Here, I'm here.
Okay.
Yeah, so you put here polynomials, or actually these are monomials. Yeah, but yeah, okay. These are polynomials. Do you have a comment or question?
I was like, maybe to make it more clear, you can write C1 exponent 0 in the integral so that we can see.
Okay, I'm trying to see one. Okay, we can. Yeah, you see, it's taking this to an, yeah. I did not write this because this is a vector. Yeah. So I don't think it's clear when I write a vector to a certain power.
Okay. But for me it's clear, at least.
Yeah, so, but this is, I mean, I was just trying to indicate what we mean by an order. So order 0, it's not that we multiply by 0, but we multiply by something taken to the power of 0. Yeah?
Yeah, it makes sense.
Okay,
I did understand
maybe
that. Maybe
this is trivial, and I'm spending too much time on this thing here. Okay, so going to velocity. Velocity is u integral over c1 f c1, and this multiplied by xi1, and usually we divide by rho, and then we integrate this, of course, over all of xi1. And this is first moment. And since this is a vector, there are actually three of them. Yeah? So, and now you can come to, I mean, we later will spend a lot of time with these things. I'll just write down one here. This is the temperature, xi1 over f xi1. So this is a little bit distinct from the energy, but this is something like the energy. What we do here is xi1 minus u. So u is the velocity, obviously the center of mass velocity, yeah, so the average velocity in a certain place. So xi1, so that's the velocity that we can actually compute here. The macroscopic, I wanted to say macroscopic. So xi1 minus u, so velocity square, and this divided by rho and d, where by d we mean d is the number of dimensions. And this turns out to be the velocity if we integrate it over xi1. Okay, now comes the very interesting part. Can you still handle something interesting? Okay, then we'll continue on the next page with something that is very important, which is a very important discovery in physics. And if there had been you're right. So if there had been a Nobel Prize in the 19th century, this is what Boltzmann would have gotten it for. The so-called ether theorem. Does everybody know what the ether theorem is and what is its significance? Does anybody know what the H theorem is? Yeah, it has
no.
Okay, what?
No, I read it somewhere, but I know.
Okay, so you read something about the H theorem, right?
Yeah, I
so
read it like
a problem
a lot of times.
That we do not have any audible recordings of Boltzmann. We only have his writing, and in his writing, he's using this, this letter, and then there's a lot of discussion whether he meant H or ether. And the interesting thing, so in Germany, so the people who are able to read what Boltzmann wrote, because he wrote it in German, they usually think he meant ether, and in the international context, it is more like, okay, so this is an H, so say this is H theorem, yeah? So we think that Boltzmann, so why would he use H in the first place? So ether is something like an E, so it's used for describing energy-like stuff, and this is what Boltzmann probably wanted to do. So this is not an energy and it's not an entropy, but it's related to this. So Boltzmann tried to find a functional that would help him to describe in what direction collisions would change the distribution. Yeah? And this he discovered in this ether. So the idea roughly was that he thought there should be a point where collisions don't matter because the loss term and the gain term are the same. Yeah? So when you come in with a certain kind of distribution, with a specific distribution into the collision, the outgoing collision would be the same, and if this is the case, then nothing would change ever, right? So, and this is called then the equilibrium. So if gain is equal to loss, then the distribution does not change. And then we say that the distribution is in equilibrium, or the system is in equilibrium. When the system is in equilibrium, the outcome of collisions statistically is the same as what is going into the collisions, and then everything stays the same. So, and this is exactly what happens if something is in equilibrium. And kind of a little bit an observation is that if you leave stuff to itself, it goes to a state where finally it doesn't change anymore. Yeah? So things seem to be going toward equilibrium. And to understand this, we look at this here. Maybe since I'm taking over time anyway, this is from the 19th century, and there is of course a mystery here, because the Newton's laws were well understood, and now you think, okay, if there are particles that do this collision and so on, so billiard balls, then the worldview was more or less, if you know the velocities, you turn everything around, so everything goes exactly back where it came from. Yeah? So, and in particular, if you look at the Newton's laws, you could always go to negative time if you just inverse all the velocities. Yeah? So, and so time seems to be time seems to be symmetric. Right? So there's no reason why anything should go differently in one way than in the other way. So the big mystery was, why doesn't this seem to be the case in the real world? Why do we notice that things change in positive time in another way than they were previously? Yeah? So why don't you get suddenly younger, yeah, jump into your mother and, go everything back, yeah? So why does there seem to be a direction toward this? So this is what we're interested now. Let's, for this, declare equation 1,1 as the collision integral, Xc1. So collision is a change, is of course change of the distribution, of the probability distribution in time. And this is given by this integral. Now I just write b. If now we are saying that this is in equilibrium, so this is the gain term in equilibrium minus f the loss term, so multiplied f2 equilibrium, and we integrate this over Xc2 and all the directions. So now I should have 1 and 2, and what I mean by this is f1. Yeah, so I have a lot to write, so I take some shortcut, right? So f1 dash is defined as f c dash. Yeah? So in order to understand why things and how things are going to equilibrium, Boltzmann defined a funny function which it is, I believe, not completely clear how he came up with this. So he defined this function ether of t to help identifying the equilibrium. By the way, the thing here is called a theorem because we can prove it, so it's not a theory. And the form of this function, how Boltzmann came to this function is not important. And actually how the function looks like is also not really important. What is important, that there exists a function with this property that we will see. Yeah? So this is why we don't actually care how Boltzmann came to this. So he kind of invented a function that is the integral over the distribution. Why do I write? Of the distribution times the logarithm of the distribution. And this he integrates over the entire velocity space and the entire universe. Yeah? So all the velocities, all the universe. So the system is the universe with all velocities and all spaces. Okay, f times log f. Yeah, so this was his idea. That's the integral over all microstates, microvelocities, and all coordinates. So it is the universe. See, this makes this function a little bit difficult to actually compute because it's an integral over the universe. Okay. Now, what happens if we take the time derivative of this? We put this 1.2, take the time derivative of this guy, of this ether. I don't get... I mean, I believe I put my status in occupied, but so what we can do with what we can do here is we can take the time derivative into the integral. So if we take the time derivative into the integral, then we have to use what is it called, the distribution. When we have several, the product rule, right? The product rule, yeah, of the differentiation. So first is we have here d. We have df1 on. So we first have this guy times the logarithm of f1. So we have first taken the derivative of this. So this end gives us the and the collision operator, and if we take the time derivative of f, so with the chain rule we get f divided by f, which is 1. C1 and dx. So this thing here in front, this is the collision operator, because it's the time derivative of f. So, and with this, there is the conclusion already. I just have to prove it. Is a not what do I say? Is a theorem, not a theory. Yeah, it's a theorem because we can prove it. Otherwise, it would be a theory. So the theorem is this time derivative is smaller or equal to 0, and if this is true, then there is a direction of time. Yeah, so there is something in the universe. We can define a function in the universe that is always decreasing. Right? Actually, it doesn't matter how this function looks like. It's only important that it exists in order to give time a direction. Yeah? So if time has a direction, the only thing that you have to prove is that there is something that gives time a direction that is not symmetric in time. Okay? So, and the question, of course, is now why? Okay, and in order to see this, we put the collision operator in the function that we have just derived. So we put the collision operator in this here. Yeah? The collision operator in this here, this gives us equation 1.3, where we have d is by dt is equal to now, okay, I have a lot to write now, so how many integrals? I think it's 4 integrals. Yes, it's 4 integrals, of which all are vectors. So in principle, this is 4 times 3, so it's 12 integrals. Yeah? So I just put 1, okay, instead of all 12. Okay, so there's a, this collision kernel B, which I just write as B here. So F1 dash F2 dash, so the gain term minus the loss term. So this is the collision operator, and this is added here. So we have f divided by f, this is 1, plus the logarithm of f1. So integral over C1, C2, all space, all directions, okay? Now what can we do with this? One thing is we can, the particles, the particle 1, yeah, and the particle 2, because they are undistinguishable, they are the same. Yeah? So they have the same distribution. So we have F1 and F2 are interchangeable because particles are undistinguishable, which means I can write exactly the same equation by just exchanging 1 and 2. So 1.4 d isa by dt is equal to the integral b. So in this here, I don't need to exchange them, yeah, because it's just the order in which I would write them. Doesn't matter. The only way where it's matter is the logarithm of f2. So, and we integrate over everything anyway, so we can just keep the same integral. So the only thing that is different here is this, right? So what we do then is we can add 1.3 to 1.4, which means now we have 2 d by dt is equal to bf1 minus this here. So now we have done it twice. So then there's here 2, and then there is logarithm of f1 plus logarithm of f2 of f1, sorry, logarithm of f1 plus logarithm of f2, and this is logarithm of f1 times f2, obviously. So this is log f1, f2, and integrated over everything again. And I have to get a new page. Okay, now we still can't interpret this, so we do something more. Namely, we decided that, we did not, okay, we did not decide this, but collision, okay. Collision is symmetric. I mean, this was anyway the proposition in the 19th century. Yeah. So you think if everything is Newton, yeah, and so particles coming this way and going out this way, so you can change them in their direction or flipping their direction, and then they would do exactly the same otherwise. So it's an important idea now that we assume that the collisions are symmetric. Yeah, so that we can just turn everything around and everything will turn, and everything outcome will get to income. So can go forward and backwards. Which means we can exchange so the after collision part, with the pre-collision part. Yeah? So, and this leads to 1.6 to d by dt is bf1 f2 f1 now dash f2 dash, so I've exchanged this here, times 2, and I have to exchange it here again, the logarithm f1 dash f2 dash, and then there is this 1 to dx sigma. Okay, so this is also true. And what we can do now is to put the equation 1.5, yeah, which is the, did I write 1.5? I think I did not write 1.5. 1.5 is this here, yeah? 1.5 is this here. So we can have 1.5 plus 1.6. So then we have 4 times now d by dt is b. So I now write again the dashed version first. So so what happens now is because the sign in this integral between 1.5 and 1.6 has changed, right? So here we have first the dash and minus the undashed, and here we have the undashed minus the dashed. So we changed the sign. This is why the 2 and this 2 will cancel each other out, yeah? And what we are left with is the logarithm of f1, f2 minus the logarithm of f1 dash f2 dash, and this integrated again over everything.
I have a question.
Yeah, wait. Okay, question?
Is this be the Boltzmann distribution function?
This is not this is not necessarily the Boltzmann distribution function. The Boltzmann distribution function is the equilibrium. This is not the Boltzmann distribution function. This is just a distribution function.
Okay, but it's somehow it has an exponential function, so that
We don't care whether this has an exponential function.
okay, but yeah, I asked this because when we are adding these terms, so we have f1, f2, f1 dash, f2 dash, and when we add them, just or the assumption is that the terms cancel and you get in the end both dash terms, right? So that's
No. Where do you see anything canceling?
because in 1.5.
In 1.5, yeah.
1.6, sorry, the last equation is f1 dash, f2 dash minus f1 dash, f2.
So we come to this equation by recognizing that everything can go forward and backward. So what has been dash is now no dash, and what has, yeah, this is the only thing, yeah? Okay? Okay, so now this leads us, so we don't do any assumptions on what f is. We just put the equation together. Yeah, we just summing up, and yet now actually we come to the magical recognition that this is smaller or larger than, smaller or equal to 0. Now is the question whether you see this. I mean, that this thing can only be smaller or equal to 0. Now the reason for this is, of course, I mean it's an integral, but if the integrand is always smaller or equal to 0, then the integral will also be smaller or equal to 0. And the integrand is smaller or equal to 0 for any f. And the reason for this is, okay, let's say y. We have to see that the logarithm is a monotonic function. So monotonic means it's increasing the same way as f is increasing, right? So that means that if f1, f2, by the way, the distribution function, they are positive, yeah? But anyway. So suppose f1 times f2 is smaller than f1 times f1 dash f2 dash, yeah? So if this is the case, because this is what we have to distinguish here, yeah? So we have these two terms up here, and whether this will be positive or negative is determined by whether the one is larger than the other. Oh, wait, I've made a mistake here. I wrote two dashes here. So this is, of course, okay, so this makes the questions, right? Sorry. Sorry, yeah. Okay. Please correct this. So, see, I mean, either of the two terms is larger, right? Okay, one thing about a distribution. A distribution is positive because, I mean, it gives the probability that something is there. So it is, so then both of these terms in itself are positive, but we have the difference between them. So depending on which of them is larger, we get this positive or negative, okay? So if this is the case, because the logarithm is monotonic, it means that also the logarithm of the same thing will behave in the same way. Now here's the funny observation. Back here we have the opposite. So we have the difference between dashed and non-dashed populations, and here we have the difference between the logarithm of non-dashed and dashed, right? So whenever the left side is negative due to the monotonicity of the logarithm, the right side will be positive. Whenever this is positive, the other one will be negative. So the entire thing can either be 0 or negative. And because this is everywhere, yeah, so the integral also can only be 0 or negative. Yeah, so this is why this here is smaller than 0, and this is smaller or equal than 0, and this proves that there is a function that provides a direction of time. And one of the most amazing of things is that this actually arises from the assumption. So there was a very important assumption that we made. We made the assumption that we can exchange the dashed with the non-dashed population. So that collision is symmetric. Yeah? Each collision in itself is symmetric, completely symmetric in time. And from the assumption that collisions are symmetric in time follows that something exists that is not symmetric in time. Yeah? And then there is, and from this comes the error of time. So from the assumption of, symmetry in time means reversibility, so reversible collisions. Arises the irreversibility of a system. Because irreversibility, if there is anything in the system that cannot be undone, yeah, then the system itself can never be going backwards. Yeah? So the irreversibility of the system. Now there is one important case. I think this is something that just popped out of this, and this was not what Boltzmann was originally looking for. He was looking for what happens at equilibrium, because we have to look at one specific case. Okay, so the system is always the universe. Goes closer to this equilibrium, and the equilibrium is this particular case where we have d ether by dt is equal to 0. This is the equilibrium. Yeah? So collisions go backward and forward the same. And as you have said before, this is not important, and this is not what Boltzmann intended, but this is, I think it's not what he intended, because he messed it up. Boltzmann messed this thing up because he defined the negative as the negative entropy. Yeah, I mean he was just looking for a function, and the way he defined it was he defined it with the inverse sign compared to the entropy. Yeah, so it's the entropy, but he got it with the inverse sign. I've taken 25 minutes over. Does anybody, wait, I stop the recording and then I ask for questions.